When people ask, what if black holes are dark matter? I treat it as two separate questions. First, could the dark matter be made of black holes in principle, without breaking what we already measure about gravity, spacetime, and cosmic expansion? Second, if it could, what kind of black holes would they have to be, and how would we catch them in the act? Because dark matter is not a label for stuff we haven't found yet. It is a very specific pattern in the universe. It behaves like matter that gravitates, that moves slowly compared to light, that clumps and that does not collide or radiate much. We infer it from how galaxies rotate, how galaxy clusters hold together, how gravitational lensing bends background light, how the hot gas sits in clusters, and how the early universe left its imprint in the cosmic microwave background. Dark matter is a gravitational actor with a well-measured script. The open question is what the actor is made of. Let me start with what we mean by black holes in this context. There are the black holes made by dying stars, usually a few tens of solar masses, maybe up to around 100 in special cases. There are supermassive black holes in galaxy centers, millions to billions of solar masses, which we know exist because stars orbit an invisible compact mass and because we see accretion disks and jets. And then there is the speculative category, primordial black holes, which would form not from stars but from extremely dense regions in the early universe, long before the first atoms. If black holes are the dark matter, the only plausible candidates are primordial black holes, because the stellar and supermassive populations we already see are far too rare. If I take the mass budget of a typical galaxy and try to build its dark halo out of ordinary stellar black holes, I immediately run into a simple accounting problem. You cannot make that many stellar black holes without first making that many stars, and those stars would have produced light, heavy elements, and feedback that we would notice. The universe's chemical enrichment and background light do not allow you to hide an entire dark matter halo's worth of star formation. So the serious black holes as dark matter idea is really primordial black holes as dark matter. And primordial black holes are interesting because they are not a new particle. They are a gravitational object. They would interact almost purely through gravity. That sounds like dark matter. But dark matter is not just invisible mass. It has to fit the universe at many times, during the first few minutes, during recombination when the cosmic microwave background formed, during the growth of galaxies, and today. The reason we think most dark matter is cold is that the small-scale structure of the universe exists. If dark matter were too fast, like light neutrinos, it would smear out small clumps early on, and we would not get the observed abundance of small galaxies and the detailed pattern in the cosmic microwave background. Black holes, being massive, would be cold. They would move slowly once formed. So on that score, they look compatible. But there is another requirement that is easy to miss. Dark matter in the standard picture is not just cold. It is also effectively smooth on very small scales in the early universe. It has tiny density fluctuations, seeded by inflation, which then grow. If instead the dark matter were made of discrete, relatively massive objects, like black holes, you introduce extra granularity. Imagine replacing a smooth fog with a swarm of heavy pellets. The average mass can be the same, but the statistical noise changes. That noise affects how structure forms and how gas collapses into the first stars. So even before I talk about direct searches, there are cosmological constraints that come from the early universe behaving too cleanly to tolerate too much lumpiness at certain masses. Now, how do we actually know dark matter exists? The cleanest line is gravitational lensing, because lensing does not care what the matter is made of. It only cares about space-time curvature. When we map the mass in galaxy clusters using lensing, we find far more mass than the luminous matter. The bullet cluster is a famous example because the hot gas, which contains most of the normal matter, is slowed by collisions while the lensing mass passes through. That tells me the dominant mass component is collisionless, or at least much less collisional than gas. Black holes would pass through like that. So the bullet cluster does not rule out black holes, but it does not uniquely point to them either. It points to something that gravitates and does not behave like ordinary gas. The cosmic microwave background adds a different kind of evidence. The tiny temperature fluctuations in the CMB encode the mixture of matter and radiation at recombination. The heights and positions of the acoustic peaks tell us the baryon density and the total matter density. From that, we infer that most matter is not baryonic. That is a deep point. Dark matter is not just dark baryons. It is non-baryonic in the standard interpretation. Primordial black holes, however, are tricky here. They are made of mass energy, but not of baryons in the usual sense. If they formed before baryogenesis or independent of baryon number, they could contribute to the matter density without being counted as baryons. So primordial black holes can in principle be non-baryonic dark matter, even though they are not a new particle. That is one reason the idea stays alive. So what would it take for primordial black holes to be all the dark matter? I need them to have the right abundance and the right mass distribution, and I need them to evade a long list of observational constraints. Those constraints come from multiple angles, and they are powerful precisely because black holes are not subtle gravitationally. They bend light, they perturb orbits, they accrete gas under some conditions. They merge and make gravitational waves. If you put enough of them in the universe to make up the dark matter, you cannot completely hide their side effects. One major constraint is microlensing. If a compact object passes in front of a background star, its gravity can focus the starlight and cause a temporary brightening. This is not science fiction. Surveys like MACHO, EROS, and OGLE monitored millions of stars, especially in the Magellanic Clouds and toward the galactic bulge, looking for these events. They were originally motivated by the idea that dark matter might be made of MACHOs, massive compact halo objects, like faint stars, brown dwarfs, or black holes. The result was that in a wide range of masses, compact objects cannot make up all of the Milky Way's halo. If you had too many black holes of, say, around a solar mass, you would see too many microlensing events. The fact that we do not strongly limits that possibility. But microlensing is not one number. It depends on mass. Lower mass objects produce shorter events that are harder to detect. Higher mass objects produce longer events that require long monitoring baselines. As surveys improved, the excluded mass ranges expanded. There are still windows where constraints are weaker, but those windows have been shrinking as data accumulates. Another constraint comes from the fact that black holes are not just point masses. They are compact, and that matters. If you fill a galaxy halo with black holes of, say, tens to hundreds of solar masses, those objects gravitationally scatter stars and star clusters. Over cosmic time, they would heat stellar disks and disrupt fragile structures. We observe thin disks and long-lived star clusters. That limits how many massive, compact objects can be roaming through halos. Similarly, in dwarf galaxies, the stellar distribution is sensitive to heating by massive perturbers. Too many heavy black holes would puff up the stars more than we see. On even larger scales, there are constraints from the early universe. Primordial black holes, if abundant, can affect the thermal and ionization history by accreting gas and emitting radiation. That radiation would leave imprints on the CMB. The details depend on messy astrophysics of accretion, magnetic fields, and feedback, so these constraints have uncertainties. But they are not negligible. If you postulate a universe full of black holes in certain mass ranges, you often predict too much energy injection at early times, which would smooth or distort the CMB in ways we do not observe. There is also a very clean constraint at low masses: Hawking radiation. Small black holes evaporate. The smaller the black hole, the faster it evaporates. A black hole with a mass around 10 to 12 kilograms would have a lifetime comparable to the age of the universe. Anything much smaller would be gone by now, and its evaporation products would contribute to gamma-ray backgrounds and other signals. Observations of cosmic gamma rays therefore rule out primordial black holes below certain masses as the dominant dark matter. So black holes as dark matter cannot mean tiny black holes. They would have already evaporated or would be producing radiation we would see. Then there is the gravitational wave angle, which became real science with LIGO and Virgo. We have detected mergers of black holes with masses of tens of solar masses. That revived interest in primordial black holes, because those masses are not impossible for stellar evolution, but the merger rates and the mass distribution spark debate. If primordial black holes were a significant fraction of dark matter, they would naturally form binaries in the early universe or later through dynamical processes, and they would merge over cosmic time, producing a stochastic gravitational wave background and a merger rate that we can compare to observations. This is one of the most active areas because it ties a dark matter hypothesis to a measurable signal in a new channel. But it is also complicated. Astrophysical black holes from stars also merge, and their formation depends on metallicity, star formation history, and dynamics in clusters. So gravitational waves are a constraint and a clue, but not a simple yes or no test yet. If I step back and ask, what mass would primordial black holes need to have to slip through everything and still be all the dark matter? The honest answer is that only narrow possibilities remain, and even those are under pressure. There are mass ranges where constraints are weaker, for example, around asteroid mass scales in some analyses, and possibly around certain stellar mass ranges depending on assumptions. But the trend over the last decade has been that it is hard for primordial black holes to be 100% of the dark matter across a broad mass function without conflicting with something. Many researchers now consider them more plausible as a subcomponent, maybe a few percent, rather than the whole thing. That is not a dismissal. A few percent of the dark matter is still an enormous amount of mass, and it could have interesting consequences for structure formation and for gravitational wave signals. Now, I want to connect this to dark energy and cosmic expansion, because dark matter is not just a local galaxy problem. It is part of the global energy budget of the universe. In the standard cosmological model, the expansion history is driven by radiation early on, then matter, then dark energy at late times. Dark matter acts like matter. Its energy density dilutes as the universe expands, roughly as 1 over the scale factor cubed. Black holes as non-relativistic mass would do the same. So if you replaced particle dark matter with primordial black holes, the background expansion history could look almost identical as long as the total matter density is the same. In that sense, the supernova data and the large-scale expansion do not directly tell you whether dark matter is particles or black holes. Dark energy dominates the acceleration today, and that acceleration is measured through distance redshift relations and the growth of structure. Dark matter affects growth strongly. Dark energy affects growth by changing the expansion rate and by possibly having its own clustering properties, which in the simplest case, it does not. If dark matter were black holes, the growth of structure could differ subtly because of that granularity I mentioned. That is where the expansion story and the dark matter story meet. The universe does not just expand. Structures grow inside it, fighting expansion with gravity. Any change in the microphysics or macrophysics of dark matter can alter that growth. This also matters for the fate of the universe. In a dark energy-dominated universe, if dark energy is a cosmological constant, expansion accelerates forever. Galaxies outside our local group eventually recede beyond our horizon.